Hey guys, this is Shaan, one of the software team leads for the 2020-21 school year. In this video, we're sort of going to go over the goals of the software team and how all of the different packages sort of fit together, all the code that we've written in our code base as of now, how they all sort of interact with each other in order to make sure that the robot is the best equipped to handle the Robo Sub challenge. As you all know by now, the RoboSub challenge involves, us making a robot that is fully autonomous and capable of doing certain things. So, for instance, it needs to be able to, move through a gate, or it needs to be able to interact with some objects or move past obstacles. So these are all challenges that the robot has to handle on its own, right? Because everything is autonomous, there's no human input allowed. All the decisions have to be made by the robot itself. All of the sort of tasks need to be handled, solely by the robot. So that's sort of the main challenge that the software team is sort of tackling. And we like to boil this down to two questions. So the first one is, what do we do? Like, what does the robot have to do at any given time? So for instance, if we see a gate in the distance and we know that we have to go through that gate in order to get points, the robot has to make that decision itself. It has to say, okay, let's move through the gate, or okay, let's go, launch a torpedo, let's go pick up an object, drop a ball, etc. So that's the first question: is like, what do we want to do? What decision do we want to make? And then the second question is, how do we do it? So the actual process of completing the tasks that we have at hand. So for instance, with our robot, we know that it has a certain amount of thrusters, and actually we can see them in the projects tab right here. So we've been using Cthulu for the past couple of years, and we're going to use it this summer as well. But we know that Cthulu has 8 different thrusters on it, and say for instance we need to move to a certain point. We've determined that in order to get through the gate, let's move forward or move to the side, however, whatever it is. So we've already made the decision, but we need to actually tell the thrusters how much they need to spin in order for us to get to where we want to go. Or say for instance with the torpedo launching, once we've gotten to the point that we need to go to, how do we actually tell the torpedoes to shoot? How do we tell the robot to shoot the torpedoes? So that's sort of an example of how does the robot actually do the things that it decides to do. So everything can sort of be boiled down into these two questions, and that's sort of what the software team is aiming to tackle. We're going to dive into our code base and take a look at all the different packages that we have and what exactly each of them is responsible for, how they interact, and so if you don't know this already, you can navigate to our GitHub just by searching Duke Robotics GitHub, and it should be the first link that pops up. For the robot, really the main sort of repository that we use is this RoboSubROS repo. It essentially houses all of the code that we need for testing the robot, running the robot. Everything that the robot needs is housed in this one repository. So that's the main one that we're going to be looking at in this video. So if we take a look, if you're unfamiliar with GitHub, this is just essentially a folder with a bunch of different folders and files inside of it. So we're going to go through most of them. For now, we're just going to be looking at these two folders in particular, the land side and onboard folders. Everything else is sort of meta. You don't really need to know about them in order for the robot to work. So stuff like continuous integration on GitHub, all of our Docker containers, stuff like that, build scripts. If you're interested in them, then definitely come talk to one of the sub-team leads about it, but we're not going to cover that in this video. One thing I do want to point out is these two Markdown files. So we have a README and a contributing. So in the README, if you just scroll down, is the first thing that pops up. If you're ever confused about a certain package or just in general how to run a command, whatnot, then this README sort of goes through all of it. It details our entire software stack, all of the flow of information, and then it goes on to running our code, running our robot, pool testing, etc. The contributing.md is just for if you want to contribute to this code base, then take a look at that. Make sure you sort of know exactly what's going on there. Not super important, but just some resources that I wanted to point out in case you ever have any questions and you can't get in contact with someone else. Yeah, just keep those in mind. The onboard folder. So the onboard folder has 10 different packages. Each of these folders is its own package. And all of these packages, when put together, can answer those two questions that we posed earlier. What do we want to do and how do we want to do it? So we're going to take a deeper look at each of these 10 packages and see exactly how they fit together and what exactly they each do by themselves. First few packages that we're going to take a look at all involve determining the state of the robot. So we're going to use this term a lot. I'm sure you've heard it in meetings already. But when we refer to state, pretty much what we're referring to is where the robot is, like what is its current status, in the context of the world, in the context of itself, where is it, like what is it doing, stuff like that. And if you think about that, that's really important when you're making a decision, right? Because, say for instance, in a human sense, I want to go to the store. Well, the path that you're going to take to get to the store is going to be different based on where you currently are, obviously, right? So intuitively, it makes sense that we need to know where we are at the moment in order to make a decision about where we want to go. So the first sort of package that we're going to look at involving state is the datapub package. So if you're not familiar with the ROS sort of structure of how packages work, then I'd point you to the ROS wiki or our own ROS tutorial, which you probably already have taken already. But for the purposes, we can sort of go through really quickly exactly how each of these packages works. So you'll see a couple of folders, launch and scripts, in most of these packages. And then you'll also have some more files. You don't really have to worry about these three files. They're sort of meta and don't really do much. But if you're more interested in learning about how to actually make these files, then definitely look into ROS, creating custom ROS packages. But for our purposes, we don't really need to cover these. Each package will also have its own README. So if you're ever confused about what a certain package does, just take a look at the README. If you don't get an idea from that, then let us know, because that's the main purpose of these READMEs is to sort of give you an overview of what exactly the package is doing. So yeah, always take a look at the README if you're unsure. Just another resource to keep in mind. But yeah, so we'll have most packages will have a launch folder and a scripts folder. So let's take a look at the scripts folder for the datapub package. So when we say datapub, this is essentially sort of the interface between, or one of the interfaces between the electrical team and the software team, right? So the electrical team is responsible for all of the sensors that are on a robot, right? And so when we're talking about state, we have to have sensors that can determine, where we are, or sensors that give you, input about about what the robot is doing at the time. So we have the DVL and the IMU on the robot. So I'd point you toward the electrical video if you're confused about what either of these do. But for our purposes, they're just two different sensors on the robot that can sort of determine the position of the robot and the velocity of the robot. So for instance, if we know that if we're moving, if the robot is currently moving, then the DVL and IMU will tell us where we are and how fast we're going, which is absolutely necessary for the other systems on the robot. So that's sort of what those two sensors are doing. And what this code is doing, if we take a look, is it's really just reading that raw sensor data in and republishing it in places that we can sort of look to that already have the correct processing done. So like, for instance, the raw DVL data, we might not know, like someone on the software team might not know how to parse the raw data. So instead we republish it into this ODOM message. And if you look at what a ROS odometry message is, it's a position and a velocity essentially. So like we can see here that we're setting a position and setting a twist, and then we're just publishing that. So really this is just making that state data available for other packages to use, making that sensor data available. So that's sort of the main purpose of the data pub folder. And as we get more sensors that can help us determine state, then we'll add those scripts, add the scripts for reading those sensors in to this package. So as we see, we also have a pressure sensor. If we decide later that we want to add more sensors, then this is the place to do it. So sort of in that similar vein, we have the RoboSub description package. So as you can see, well, this one is actually a little bit different. It doesn't have any scripts or launch files. This is sort of just a package that has a little bit of information about the robot itself. So if we take a look at the meshes folder and we open this STL file, we can see that it's sort of a low poly representation of our actual robot, right? So this is really useful for certain transformations that have to be done, which we'll get into in a bit, but also just for like visualization. I think this might be used in the simulation. It's just information about the robot. And this doesn't change once we already have a robot, right? If we have a different robot in the future, which we probably will, then we'll have to remake this file. But for our purposes, this is the representation of the robot that we're using at the moment. And then in this folder, we also have an URDIF file. It's sort of a similar idea, just like a 3D representation of the robot. And yeah, that's really all the RoboSub description has. We'll see that these 3D representations are actually used in another package to help us determine the state of the robot, but we'll get into that in a second. The package we're going to look at is the static transforms. So all that the static transforms does is it defines a bunch of different coordinate systems and creates transformations that allow you to sort of switch from one coordinate system to another. So that might not seem very intuitive at first, but essentially think of it like this. So our robot is in a pool, right? So from a global sense, we can see that the robot is moving, left or right, or it's moving, up or down, right? So that's sort of the global X, Y, and Z coordinates, right? From where we're viewing, if we're standing stationary and observing the robot, we can see it moving in a 3D plane, right? But in terms of the robot, its local coordinate system is actually different than the global coordinate system. Because the robot doesn't have a GPS, it doesn't actually know in the grand scheme of things where exactly, how much it's moved, right? It doesn't know how much it's moved north or south, east, or west, which is what the global coordinate system is. So in order to actually determine where it is globally, we have to transform its movement from its own local reference frame, which is defined by this sort of, by these axes that we have here. So for our robot, we have this big bundle of wires that come out the front, and for the CS team's purposes, that bundle of wires always points to the positive X direction. And then from there, you can use the right-hand rule or the same coordinate system to determine what the local Y and Z planes are as well. So what these transforms allow us to do is they allow us to go from, say, that local frame to a global frame very easily. And if we actually look at the launch file, this is the only code that's actually in this package. We can see that it's just creating a bunch of different transforms. So this is something that's built into ROS. And if you're interested in this, there's probably a wiki page about it. But essentially all we're doing is we're giving it a name and then some position. This is probably in meters. So what point are we trying to transform to? That's what these arguments are relative to a certain relative to a different point, essentially. So that's what the static transforms do. And if we need another transformation, say we want to go from different points. So like here we have the corner link and the base link, like the center of mass. Maybe we want to transform to our cameras, for instance. Maybe that'll help with some vision thing that we're doing. Then we can always just create another transform that goes from a certain frame of reference to the cameras. The next package we're going to look at is the sensor fusion package. So here we see that familiar package structure with the launch scripts, and we also have a params folder just for some constants that we have. So the sensor fusion package is sort of responsible for putting all of the previous three packages together and actually giving us a final estimation of where the robot is, a final estimation of the state of the robot. So if we go to the launch file, what we can see is we have fuse.launch. So pretty much it's taking parameters from that robot description package that we have, and it's using this robot localization package, which is built into ROS. So pretty much we're loading a bunch of data in from different sources. So say for instance from the IMU and the DVL that we used, that we talked about before, as well as those transformations that we used earlier, those 3D models that we used. And we're putting all of those together to give us a final determination of where the robot is. And this is going to spit out an odometry message, which, like I said before, is essentially just a position and a velocity, right? Positions and velocities of the robot. So we're outputting that, or we're taking that output and we're telling it to publish to the state topic that we have. So if you're ever running the code and you want to know, what the robot thinks it's at, then you just do a ROS topic echo on the state topic, and it'll tell you exactly what the robot, exactly where the robot is, position and velocity wise. And then we also have something for the simulation, which we're going to talk about a little more later, but one thing to keep in mind is when we are running a simulation, there's no real IMU or DVL present on that robot, right? Because the robot is sort of virtual, right? These sensors don't necessarily exist, but we're sort of mocking them and then republishing them as real DVL and IMU messages so that they can integrate seamlessly with the rest of our code. So that's essentially what this whole script is responsible for. The final package that's sort of relating to sensors that I want to go over really, really briefly is this Avt Camera. All this is responsible for is driving the cameras that we have on the robot. So, based on our model here, actually you can't see them, but normally we would have 3 different cameras on the robot. And so this code is there for turning on those cameras and actually getting a video feed that the robot can use, that the CV team can use to make decisions. So far, all of the packages that we've talked about are sort of there to help us determine the state of the robot. So now we're actually going to start getting into those 2 questions. So what do we want to do? How do we want to do it? And the first package that I want to talk about regarding that is the motion planning, or will probably be renamed to task planning in the near future. So task planning is the code that's responsible for making decisions. So this sort of integrates all of the input that we've had from all of the different sensors, from the cameras, pretty much from everything. And this essentially says, okay, I have all of this input. I'm finally making a decision. This is what I want to do. So motion planning is the brain of the robot. It's making the decisions, based on all of the data that it's gotten. So, if we go through the scripts, the task planning team recently has sort of created their own framework for how they want to handle all of the tasks. So, for instance, let's just look at, the move tasks file. So they have a bunch of different tasks that can essentially do different things, right? So move to pose global. So this essentially just tells the robot to move to a global position. move to pose local, same thing, but in a local frame of reference, which we talked about earlier. Hold a position. So we have all of these sort of abstract classes, abstract tasks that can be used to, do whatever movement that we want, do whatever task that we want. And as we get closer and closer to the competition, we'll have more and more specific tasks. So say, for instance, there's a gate task. So that involves identifying whether there's a gate and then identifying how to move through the gate and using the move tasks that we just looked at to do that. So it's essentially this big sort of class structure where it gets more complicated the further down you go, but the framework is all here, and really the only thing stopping us from making whatever task that we want is the different sensors on the robot and making sure everything is integrated. But yeah, so in the future, we might also have like a torpedo task, for instance, or a ball dropper task. Right now, we're just focused on movement and making sure that we can sort of, get to where we want to go. But in the near future, that's sort of what our focus is going to be. And then, so that sort of briefly goes over, how we're making decisions. But then, where does task planning say, okay, move to pose local? That's saying that we need to move somewhere, but what's actually moving us to that point? And that's where controls comes in. So controls answers that second question of how do we get there, or how do we do something? So controls is responsible for taking an input, so taking a desired sort of thing to do, so move to a global position, move to a local position, or move at a certain speed, whatnot. And it says, okay, I know where I want to go. I know where I am from all of the other state republisher topics that we've talked about earlier, or all the other packages that we talked about earlier that give us the state. So if I know where I am and I know where I want to go, I'm going to determine, or controls is going to determine the thrusters that we need, the movement that we need in order to actually get to where we want to go. And so that involves some, PID algorithms, some controls algorithms, but essentially that's what's telling the thrusters how fast to spin in order to get, to the end goal. So there's a lot of different scripts in here. If you're interested in, what each of them do, I'd recommend that you, hop into a controls team hop in with the controls team during one meeting, and we can go over it with you. But really all that it's doing is it's saying, I'm taking the desired state from task planning. They're telling me where I want to go. I'm taking in the state from the sensor fusion that we talked about earlier, and I'm just putting those two things together, doing a bunch of math, and then figuring out, how much to spin each of the 8 thrusters on the robot to get to where we want to go. I sort of glossed over exactly how task planning makes decisions on which tasks to do. And that's one of the aspects that CV sort of comes into play. So CV stands for computer vision. As I said before, there's 3 cameras on the robot, and they're all constantly publishing an image feed that we can use to make decisions. So say, for instance, our left camera detects an object, and we think that object might be a gate. Then task planning will say, okay, let's do the gate task with that object in mind. But actually determining what an object is not a simple task. And that's where that's one of the responsibilities of the CV team. So if you think about it, our robot is underwater, visibility is kind of limited. Our camera is not going to have the clearest, picture. So what the CV team has done is they've trained a machine learning algorithm to detect objects based on a bunch of training images. So with a certain amount of certainty, if we see, an obstacle in front of us, we can determine, hey, is that a gate that we need to go through? Is that a buoy that we need to navigate to? Or is that just something in the water that we don't want to hit? So that's the responsibility of the CV team, is getting that information to task planning. So once we've determined what an obstacle is, if that information is relevant and important, it needs to be published somewhere so that the other teams can use that information to make a decision. And sort of the way that what CV is working on currently is getting a sort of 3D representation of these images, so that we can we can have an easier time with determining how to get to certain obstacles. Right now, we sort of have bounding boxes. So if you imagine a 2D screen and you see a gate in it, we can outline that gate, but we don't necessarily know where it is in the grand scheme of things, because a 2D flat plane isn't the same as 3D real life. So that's sort of what the CV team is working towards right now. And once they get to that point, task planning will be able to create those gate tasks and buoy tasks, and we'll be able to execute those. The next package is offboard comms. So when controls determines what thruster speeds to publish, they publish a 8x1 array or a vector that has a bunch of different values in it. Where do those values go? How do those get to the thrusters? So I'm sure in the electrical video there will be a little bit more detail, but for our purposes, the thrusters are connected to an Arduino, and the Arduino is relaying the information from controls to the thrusters. And so in order to do that, we need to have driver code that listens to the topic that controls is publishing to, and then translates that to the Arduino so that the Arduino can then tell the thrusters what to do. So this offboard comms package is sort of that pipeline to do that. And yeah, if you're more interested in how the Arduino is working exactly, definitely watch the electrical video or speak to one of the sub-team leads about that, and we'll be able to give you more information about that. All right, the final package in the onboard container is the execute package. So far we have a bunch of different packages, and they're all sort of doing their own thing. How do we make them all run at the same time without having to run 10 different commands? We don't want to ROS launch controls, ROS launch task planning, do all that stuff. That's way too much work. So what the execute package does is it consolidates all of that into separate launch files or single launch files that can handle everything that we need. So if we take a look, let's take a look at motion.launch. This is the launch file that does everything that we need it to do. So if we look at what exactly it's doing, is it's launching state.launch and controls.launch, right? So state and controls, and then eventually it'll also launch task planning once we've tested that in the pool. But if we look at state.launch, this has all of the sensor fusion stuff that we were talking about, all of the data pub stuff that we were talking about. So really this is consolidating everything into one place so that we can really easily test stuff without having to worry about, did I forget a command, and stuff like that. So the execute package doesn't have any actual scripts. It's just launch files for driving the rest of the robot. Yeah, and with that being said, that's everything in the onboard container. I know this video is getting kind of long, but really quickly, I just want to go over what's in the landside container. So this is stuff that's not quote unquote necessary for the robot itself. So when we're at competition, we might not be using anything in the landside container. We might just be running stuff on the onboard container because it's fully autonomous, right? So if you think about landside, it's stuff that's running on your local machine. So really it's mainly used for testing purposes. And we can see that in these three packages, that's what they're for. So the main thing is the simulation. The simulation is incredibly important, especially while we're all virtual, because it allows us to test stuff without actually having to physically run the robot, right? I don't know if you're familiar with it, but pool testing is something that takes a long time. It takes a lot of setup, a lot of logistics involved. So being able to just run something in the simulation whenever you want is really, really important. So I'm not going to go super in depth to how the simulation works. It's a really, really big project, and I encourage you to talk to Maverick or whoever the team lead for the simulation is at the time. But if you need help getting set up, then there's a README here. There's a lot of information. You can talk to anyone on the CS team and they'll get you to the right place. But keep in mind that this simulation is how we do all of our testing, pretty much all of our testing, especially recently. Yeah. Other than the simulation, we have a joystick package. So obviously we don't use a joystick during the competition because, well, the robot's autonomous. We can't really control it. That's not allowed. But it is useful for testing. So say when we're testing controls, making sure that the thrusters can spin, stuff like that. If we want to, get a certain camera view from the robot, we can use the joystick to just, spin around in a circle or whatnot. So that's what the joystick is used for, not for the competition, but for testing purposes. And then the camera view is sort of necessary for getting the video feeds onto your local machine so that you can actually see what the robot is seeing, while it's seeing it. Yeah. But really the land side, mainly used for testing, doesn't necessarily need to be running, but still really important nonetheless. Yeah. And with that being said, that's pretty much everything inside of our code base. If you have any questions, feel free to, send me a message on Slack, whoever the software team lead is. If you're, any questions, any concerns, if you're interested in joining a different sub-team, then by all means, talk to whoever's leading that sub-team and just get in touch. Really, I hope that this was helpful for those of you who wanted to sort of see the big picture and how everything fits together. But yeah, your feedback is really appreciated. And yeah, thanks for watching this video. I know it got kind of long, but yeah.